Find the mass of the solid captured inside the cylinder. X squared plus y squared equals to 2y, but outside the cone, z squared equals to x squared plus y squared with density something. Okay. Alright, so first you have to think about what x squared plus y squared equals to 2y is. This is, if you subtract 2y, and then if you complete the square by adding 1 both sides, you get x squared plus y minus 1 squared equals to 1. And that's a circle centered at 0, 1 with radius 1, so this is the circle that you get. Okay? X and then y. Now, however, this is in 3D, so in three-dimensional space, you have an extra z axis, and since this doesn't have anything to do with z, for any value of z, you're going to get this circle. Now, what that means is you're going to eventually get a cylinder whose intersection with the xy plane is this circle. So if you draw this in a different perspective, the usual perspective that we draw is having x here, and y there, and then z there. We know that the circle will be cylinder, so it'll be a cylinder that's like that. Okay. Alright, what about z squared equals to x squared plus y squared? Well, this one, if you take the xy trace, well, xy trace actually doesn't do anything. Let's try the yz trace. Yz trace, that means you're setting x as 0, so you get z squared equals to y squared, which gives you z equals to plus or minus y. So z equals to y is this, the 45-degree line, and z equals to negative y is this, right? So z equals to y and z equals to negative y. And if you took the xz trace, you'll get the same thing. It will be something like this. Now, instead of taking the xy trace, let's take the level curve z equal to 1. Well, if z is 1, you get 1 squared equals to x squared plus y squared. That's a circle of radius 1. So at z equal to 1, you get this circle. If you imagine that this is your x-axis, you get this circle. And the higher up you go, if z is bigger, then you get a bigger circle. And even when z is negative 1, you still get the same circle. So what you end up with is this x, y, and z. You get this cone. Okay, so you get this cone, and what you're trying to do is you're trying to put these two together. So it'll be if you put them together, it'll be something like this. You have a cylinder that's touching the z-axis, and you get some kind of a cone. It's like this. And if you want the outside the cone but inside the cylinder, it will be something that's something that looks like this. It's outside the cone. So you take this cylinder and you chop off this much and this much, and you get some weird thing that looks like something like this. Okay, where these two parts are the cylinder that's cut off by the two cones, and this is the thing that you're trying to integrate. Okay, and let's call this region R. Now I tried to use a 3D grapher to see what the graph is. Here's the graph drawn with a 3D grapher, and as you can see, you get this cylinder and a cone, and they do intersect like this. And if you look up here, then you can kind of see how the cone is cutting off parts of the cylinder, right? So that part is gone, and therefore you get this shape that I described. So there would be these shapes that's cut off by this thing. If I get rid of the surfaces and just look at what happens, you can kind of get a better idea. It's somewhat caved in this way, right? Yeah, so it's something that looks like this, but it's partly touching these two cones, and it's also made up of this cylinder. So that's what it is. Okay. All right. So now what's the plan? Well, the plan is to integrate this using a triple integral. And when you use triple integral to integrate this, you start from this bottom cone and you end at that top cone. So you start from here and you end there, right? So my plan is to paint this region with dz inside. So dz means going up. So you start from this bottom to top, and when the z is completely integrated, then you're just left with the circular region. If the z part is just completely integrated, then you just get this part, because integrating over z is like flattening a pancake. So the entire z axis collapses down and you just get this circle. So once you integrate by z, then the remaining is just integrating over this circle, so it's kind of easy afterwards. Alright, so let's go back to that thing. Alright, so how do we represent the top cone and the bottom cone? Because we just did, from that picture, we just decided that when you have this cone, you start from the bottom part of the cone and you go up, right? And to do that, you solve this for z and realize that, well, if you solve this for z, you have plus or minus square root of x squared plus y squared, right? And the plus 1 must be the top half of the cone because z is positive, and minus should be the bottom half. So here's how we do this. Oh, and by the way you get the mass is the integral of the density, because rho times the density times the volume gives you a small mass, and if you integrate this over this strange domain that we just did, then you get the mass of the object. Okay, so that's what we're trying to do, and therefore we are integrating rho over dz dy dx, and then your your z goes from negative square root of x squared plus y squared to positive square root of x squared plus y squared. And once you're done with this, then you end up with this circular region. Actually, that's not the circle is actually this way. Here's 1 and radius 1. Okay, so you're integrating. Once you've integrated z, this is what you get. And let's not write rho, but let's write down the formula for that, which is square root of x squared plus y squared. Okay. Now, see, x squared plus y squared equals to 2y. Already you kind of see that if you integrate this, well, maybe it's not too bad. No, the thing is, when you try to integrate over this circular domain, trying to use y and x, that's going to be very challenging. So let's move on to the polar coordinates. So to use polar coordinates, we need to change this into polar, and the way you change this into polar is first change this into r squared, because x squared plus y squared is r squared, and then y is r sine theta. So let's remember this. R squared is x squared plus y squared. X is r cosine theta, and y is r sine theta. So using this, you can always go from rectangular to polar. And then dividing by r, you get r equals to 2 sine theta. 2 sine theta is the curve that's describing the boundary. And if you have that curve, and think about shooting rays from the center, and you always start from 0 and you stop when you meet the curve, right? So your r value would be starting from 0 until r equals to 2 sine theta. And also, because r is equal to square root of x squared plus y squared, all of these can be written as r. So that's nice. So let's change everything into cylindrical. Oh, and by the way, your rays will only intersect this region if it's between 0 to 180 degrees, or 0 to pi. So theta will be between 0 to pi. Okay. All right. So theta goes from 0 to pi. R goes from 0 to 2 sine theta. And then because this is negative r, and that's positive r, and then you also have this being r. And another thing that you have to remember is that dy dx is r dr d theta. So there's an extra r there. So r dz dr d theta. R squared integrates to, this is r squared, but you're integrating by z, right? So you have 0 to pi, 0 to 2 sine theta, r squared, that's a constant, so if you integrate by z, it's just r squared z, and you're plugging in r and negative r into z. So when you do plug in r, that's r cubed minus negative r cubed, so it's going to be integral from 0 to pi of 0, you still have to integrate by dr and d theta, 0 to 2 sine theta, and then this will be 2 times r cubed dr d theta. Okay, let's continue. I need some more space. So we need integral from 0 to pi, 0 to 2 sine theta, 2 r cubed dr d theta. Integral of r cubed is 1/4 r to the 4th times 2. You still have to integrate from 0 to pi, but since you've integrated for r, you still have to plug in 0 and 2 sine theta. And then d theta. When you plug in 2 sine theta here, 2 to the 4th is 16. 16 divided by 4 is 4. 4 times 2 is 8. So you have 8 times integral from 0 to pi of sine to the 4th theta d theta. Okay. Now for this, you need to apply this double angle formula twice. Sine squared is equal to sine squared of theta is equal to, or sine squared of x, let's say, is equal to 1 minus cosine 2x over 2. And you also have to know that cosine squared of x is 1 plus cosine 2x over 2. So these are needed if your power is even. If it's odd, then you don't need this formula. So it's an easier question, but this happens to be the more challenging one. Okay. So you have this, which is 8 times 0 to pi. You rewrite this as sine squared to the squared. So you get 1 minus cosine 2x over 2 squared this should be theta, d theta. And because 2 squared is 4, 8 over 4 is 2, you end up with 2 times integral from 0 to pi, 1 minus cosine 2 theta squared d theta, which is, by the way, if you expand this, you get 1 minus 2 cosine 2 theta plus cosine squared 4 theta, not 4 theta, sorry, 2 theta. And then you can now apply this formula with x being 2 theta. So cosine squared of 2 theta is 1 plus cosine of 4 theta over 2, right? So that gives you 2 times, well, let's just multiply 2 inside, so you get 0 to pi of 2 minus 4 cosine 2 theta. And this one, if you multiply by 2, it just becomes plus 1 plus cosine 4 theta d theta. And now we integrate. These are easy to integrate now. You get 2 theta. Integral of cosine is sine, but because of 2 you get 1 half. So it's 1 half 4 times sine 2 theta. And then plus 1 will integrate to theta, and cosine 4 theta will be 1/4 sine 4 theta. The reciprocal of this number should be here, right? And then you plug in pi and 0. Every time you plug in pi or 0 into sine 2 pi, sine 4 pi, that's 0. Sine 0 is 0, so these actually don't produce anything. So the only thing that does give you something non-zero is when you plug in pi into theta here, so you get 2 pi. When you plug in pi in here, which is pi. And then when you plug in 0, everything's 0, so you just get 3 pi as the final answer.